where your delta H, your negative delta H, is larger than your T delta S term. That way it would make delta G negative. All right, moving on. That is delta H, delta S, delta G. We also need to talk about reaction rates and equilibrium. So let's look at rates. A rate is how fast a reaction goes. We know inherently some processes, like decay, are really slow. Other processes, like metabolism or certain reactions in our body, happen incredibly fast. So what determines how fast or slow a chemical reaction will occur? It all has to do with the activation energy barrier. Okay, what is that? Well, if you remember, we drew energy diagrams, and you will need to be able to draw and label an energy diagram and the activation energy and delta G on those diagrams. Here is an energy diagram. We have the reaction progress on the x-axis, and we have delta G, or I should say, yeah, delta G on the y-axis, change in free energy. So if we have a reaction that looks like this, let's say here's the energy level of the reactants. They have this much energy, and this is what the rest of the reaction looks like. And so here would be the energy level of our products. And then let's say we have another reaction that looks like this. Same energy level for the reactants. Same energy level for the products. Which one is going to occur faster? Well, if it all depends on the activation energy barrier, let's figure out what that is. The activation energy starts at the energy level of the reactants. Okay, so if we draw like a dashed line, starts there, and it ends at the peak of the hump on our energy diagram. So this that I've drawn here, indicated by an arrow, that's the activation energy. We abbreviate for the reaction in black. But for the reaction in pink, same idea. We have this dotted line, so the energy starts at that, goes all the way up. And so this right here is the activation energy for the reaction in pink. So which one's larger? Well, obviously the one in pink is larger, which means it's going to be a slower reaction. The one in black will be a faster reaction. All right. So definitely know how to label the activation energy. Does anybody remember how to label, or what I should say, you will need to know how to label delta G as well. So if we look at that, that is the amount of energy between the reactants and products. So here's the energy level of our products. Here's the energy level of our reactants. Here is delta G. All right, same idea. It's going to be the same value for the black reaction because I drew the reactants and products in the same spot. Okay, and is delta G positive or negative? In this reaction, delta G is negative, so that is a favorable reaction. All right, so that's energy diagrams. Once we know about reaction rates, we realize there's ways we can manipulate reaction rates. So first one is if we increase the concentration of reactants. That would increase the rate. All right, so why would that increase the rate? Well, assuming you're in a confined container or beaker or test tube of some kind, which is where all lab bench style work is done, if you increase the concentration of your reactants, you're going to increase the number of collisions that you get. And remember, you have to have what's called an efficient collision for a reaction to take place. All right, increasing the temperature is going to cause your reactant molecules to move with more energy. We've added energy to our reactant molecules. They will collide more often because they're moving faster. and they will collide with more what we call forcefulness. Okay? And those things will definitely increase your reaction rate. Also, the addition of a catalyst. Now remember, a catalyst is a substance that's not used in the reaction itself. It's not a reactant, it's not a product. It's a third party here. Addition of a catalyst works to increase the rate by lowering the activation energy. Okay, so if we're looking at the diagram I drew up here, the pink would be like saying this one is no catalyst. And then the black one would be like saying that is the reaction with a catalyst. Because it has a smaller activation energy. Okay. Catalysts, they lower activation energy. They can help bring your reactant molecules together and orient them in the right, just the right way so that they do get a sufficient or an efficient collision when they come together. But that's a catalyst. So know those 3 ways to manipulate reaction rates. A little bit more on chapter 7, equilibrium and Le Chatelier's principle. So remember, equilibrium is where delta G equals almost 0. And what that means, it doesn't mean that nothing's happening. It means that the forward and the reverse reactions are happening at the same rate. Okay? You are making products and then you're turning around and remaking your reactants at the same rate. You are continuing to make products. So you need to know how to write the equation for K, because when you have an equilibrium, you have a value of K, which is what we call the equilibrium constant. Okay, and then based on the size of K, predict if reactants or products are favored. So remember, for any reaction, A plus, it kind of looked like this off the lecture slides, I believe. You'll have a double arrow. And if we have these reactants and these products and we want to write a value for K, K is the concentration of products raised to the power of their coefficient. So you'd have N, and then you would have raised to the power of its coefficient. Okay, and that's divided by the concentration of reactants. Okay, all raised to the power of their coefficient. Now, if your coefficient is a 1, you don't have to write that in, but if it's a 2 or a 3 or a 4, you definitely need to write that in. So here's a practice problem. It says, for the reaction of N2O4 gas, making 2 moles of NO2 gas, the equilibrium concentrations at 25 degrees Celsius are given here. 0.0325 moles per liter for NO2, 0.147 moles per liter for N2O4. What is the value of K? Are reactants or products favored? All right, so let's go ahead and calculate K. So we're going to do the concentration of NO2 squared, because it has a coefficient of 2, over the concentration of N2O4. And we don't put anything in the exponent there because there is no coefficient. So then if we just plug the numbers in, we would have 0.0325 squared divided by 0.147. So now we're just going to calculate this. 0.0325 squared, and we get 0.00106. Divide that by 0.147. Oops. 0.00106 divided by 0.147. And I got a value of 0.007 And double check me on this. You could put decimals in there. So that would be 7.14 times 10 to the power of 3. That would be our value for K. Now remember, if K is less than 1, that reactants are favored. Okay? You have more reactants than products at equilibrium. And if K is greater than 1, products are favored. Okay? But here, because our K is less than 1, reactants are favored. Okay? Last thing in chapter 7, I put a good practice problem for Le Chatelier's principle. You need to be able to predict, right, left, no change. Here's Le Chatelier's principle to remind you. It's when stress is applied to a system at equilibrium, the equilibrium concentrations shift to relieve the stress that was added. So for example 1, you can change concentration. You can increase or decrease it. You can do it for products or reactants. And so identifying how those shifts will occur is really important. We have several review things from the lecture notes on chapter 7, or again, look at that document for textbook problems that I sent out for chapters 1 through 9 or 10. Some of those chapter 7 problems would be good practice with Le Chatelier's principle. But also, in addition to changes in concentration, you can change temperature. Okay, and you need to know the sign of delta H, whether it's a plus or a minus delta H, to be able to predict this one. If you write in heat as a reactant or a product, and then if you're increasing temperature, you're increasing heat. It's like increasing the concentration of a product or a reactant, whichever side it's on. And then lastly, predicting changes in equilibrium according to pressure or volume changes. For this, you need to look at the number of moles of gas on each side. The side with the fewer number of moles of gas is the side it would shift to if you increase pressure. Or if you decrease pressure, it would shift to the side with